You have spent a lot, you have dedicated a lot because you made it to the last part of the exercise. Welcome to RadSound FRCR Physics. You remember we are following from the beam to image formation, optimization, and subtraction. So starting from the beam formation from the X-ray using the two, which is the last part, which is fluoroscopy and DSA. Now, radiography captures single moment. So let's compare both of them. So if radiography captures single moment, what about fluoroscopy? What are we doing? In fluoroscopy, mostly it follows motion in real time. So it's from F1, F2, F3, F4. This is just for illustration. So it captures motion in real time. This is powerful, but it creates a new challenge. Every live image requires radiation, meaning that image quality and dose must be controlled continuously. So as can say, we have X-ray just static, you get something once and for all. But for radio, for fluoro, it's continuous. So what is the main difference between fluoroscopy and radiography? Let's say we have started with the MA. So mostly radiography MA is higher and more short exposure. But in fluoroscopy, because of the longer time and we're capturing motion, so it is a bit lower MA per frame. So it's radiography is a single image. The other one, on the other hand, it is continuous, can be paused, just stepping and off on. Okay. The other on radiography is high spatial resolution. What means spatial resolution? Means in space, just a static something taken with a high spatial resolution in the detector. Whereas fluoroscopy mostly it values temporal resolution. What is temporal resolution? Temporal resolution means timing. So it is mostly looking at time as the time motion is moving. So we capturing timing. So we have to value. We have to get better image quality while during the time interval. So this one has a high spatial resolution. This one has highest temporal resolution. It's a priority. So in radiography, no motion tracking, whereas in the fluoroscopy, it's a bit live guidance and navigation with the wires and the catheter insertion and others, such as interventional procedures. Just diagnostic snapshot, just cumulative dose. So, example of fluoroscopy could be barium, ERCP, catheter guidance, coronary angiography, pacemaker insertion, vertebral plasty, stent replacement, and all other interventional procedures. Since we're talking about continuation, let us take a look into the fluoroscopic. So mostly we say in radiography, what does it look like? Is this okay? In fluoro, we say where does it moving toward? Where are we now? Are we in the abdomen? Are we in the lower limb? Where are we now? Okay. So lower dose per frame does not mean low total dose cumulatively. The total dose equal time multiplied by pulse rate, multiplied by field size, multiplied by the patient size also. So the larger the patient, the larger the field, the higher the pulse rate and the timing, also a geometric mode. All of them cumulatively will give us the cumulative dose for fluoroscopy. So fluoroscopy could be a bit higher dose if not well monitored. Despite all the monitoring, mostly fluoroscopy will have more high dose than radiography. So most of the older methods are using like continuous plus code, but nowadays most of them using paused mode. Okay, what's the difference? In paused there will be a bit slower. Okay, the motion will be a bit slower, and the dose will be less. So, for example, take a look. We have 30 pulse per second. The motion is going to be smooth. Okay, the motion is going to be smooth. But what about the plural? And like if the frame decreased by half, so we have 15 pulse per second. So a bit smoother but high dose because number of frame increases. You can say now at the frame of almost we have like four. You can say now we have four of them. So the dose would be more than half of that 15 compared to the 7.5 pulse per of frame per second. In this part, we can have lower dose or half the dose if the other parameters are being monitored. So we have lower dose, but the motion is going to be jitter a little, so a bit problems. We are trading off. If the prem is 3, half of 3.5, so usually the prem is going to be choppy motion, but the lowest dose. If the other parameters such as the size of the patient, the timing taken, and everything cumulatively. If they are all being monitored, the dose is going to be less, but there will be motion problem with the motion. So you see this 30 that is a bit more smoother motion. So less pulse rate, less dose, but less temporal smoothness or temporal resolution. So pulse rate could be relation with temporal smoothness. Lower pulse rate equals less dose but choppier motion. The trade-off is temporal resolution. You have to consider both of them. So mostly we're going with the 7.5 pulse rate or frame per second because the beat have beta a bit lower dose and mild jittering in the motion also. So to trade off with the temporal resolution a little no down to 3 because the image may not be of diagnostic and the patient might be more exposed to more dose than it should be. Recap this part because it is a very important exam. If pulse rate is reduced, what happens to dose and smoothness? What will happen that the dose is going to go down, the dose will be down, but still the smoothness of the motion is going to be less. Okay, there'll be a bit jittery. So depending on which rate we have taken, whether 15 or 7.5. And at the same time, we must remember post-fluoride reduces dose only if other parameters, as we mentioned before, are also not auto increased to compensate for that less pulse. Because as you reduce the pulse rate, other parameters are going to be automatically increased in order to compensate for the low motion or to compensate for the low temporal resolution. After understanding everything, what will happen to the how can we have the image? So the image can be formed using image intensifier or flat panel detector. So these are the two types of detectors we're using in the fluoroscopy. So what is image intensifier? The structure of the image intensifier is as you can see in this place. We have input password, so we have output password, we have so the input password. What is the action of the input password? As the Romney X-ray comes, it will hit the input password. The length of the input password is around 25 centimeter, and it made of cesium iodide. So that after the Romney X-ray hit this part of the input password, the cesium iodide it will then be converted. It will convert that X-ray into transformates converted into light. So then that light will travel and hit what we call photocathode. Cathode, which is made from antimony cesium, will convert the made light. Okay, from the name photocathode. Photo means light. So photo means light. Cathode means electron. So it will convert the light which will be formed after conversion of the X-ray by the input password into electron. So photocathode is going to convert the light into electron. All right. So as that electron being converted, it's gonna hit. There are three like electrons which are made within the vacuum of the input password. We have one of them, the first one, which is G1, the electron one. Okay, we'll make them uh, control the emission of that electron. Okay, the electron coming from the photocathode. Then those electrons will go inside the main G2 of the electron will focus them toward the output. Okay, then the other one would accelerate them. So the G3, which is the acceleration, mostly use kbp between 25 to 20 to 35, and that kbp will be the same as the energy of the electron accelerating. So they are going to be accelerating with the kilo electrovolt energy of 25 to 35 within the vacuum, and then they're gonna hit the output password. The output phosphor is made from zinc cadmium sulfide, and then sometimes doped with sulfur the silver. The length of the output phosphor is 2.5, so you can say it is almost 100 times the less than the input phosphor. Electron hit the output phosphor, which made from zinc cadmium sulfide doped with the silver. They are going to be converted from the name phosphor. It's going to convert those electrons back into light. Okay. So remember, we have input passport, the image coming, at the output passport after the focal spot. So the focal spot of the image intensifier is just in front of the output passport. This is very important in exam. So at that, the image is going to be flipped and inverted. Remember this point. And the inversion, left will become right, right will become will turn to be left, and upside down, that's flipped, inverted 180 degree, is going to be corrected electronically. So as we continue, so now what will happen? We have our light coming out from the out passport. So other lights start coming out of the out passport. The light will hit what we call CCD, which is coupled with the out passport, that charge coupled device. Then that device coupling is going to take that bright light and convert them into video signal that can be converted into image, which will be displayed. Remember, the inversion is going to be corrected. The flipping and the inversion is going to be corrected electronically. Now comes the concept called brightness gain. What brightness gain? So brightness gain is a multiplication between the magnification gain and the gain flux. So what is magnification gain? Magnification gain is defined as the input, the diameter of the input, okay, the input diameter of the input passport, or the diameter of the input passport divided by diameter of the output passport. So we take diameter of the input, which is 25, over diameter of the output passport, which is 2.5. So almost it's 100 times. So mostly the brightness is going to be multiplied the 100, or the magnification gain multiplied by the plus gain. The plus gain mostly is due to the G3, which is acceleration of the electron coming from the cathode after being converted into electrons. So the electron coming traveling within the vacuum. So after being focused by G2, they'll be accelerated by the J3, so that we can have more electron reaching the output passport, converting into light. And then that mostly is around 50. So we have like the brightness, total brightness or brightness gain, multiply that 100 by 50, mostly between 5,000 to 20,000 times. So just the total brightness gain after for each one X-ray that reached the output passport. So just a really remarkable magnification, or say the brightness has been amplification. So amplification is very high. For each one X-ray to get as many as possible bright light there that can be used and to form the image that will be displayed on the monitor. Recap regarding the image transfer, because it is very important. The input passport height is mostly 25 to 35 centimeter, and we're taking 25 centimeter for illustration, and the thickness mostly between 0.3 to 0.5 millimeter, or 300 to 500 micrometer. You can take micrometer better because of the output passport also. So now the input passport is made from cesium iodide, and that cesium iodide will convert X-ray, the remnant of the X-ray, into light, and that light will be converted by photocathode, which is made from antimony cesium. That photocathode will convert the light into cathode electron, and the electron will be controlled by the G1 electrode. Then the second electrode, which is G2, will focus them within the vacuum toward the output passport. Then the third one, which is using the KBP, will accelerate them toward the output passport. Then the output passport, which is made from zinc cadmium sulfide, will convert the common electron into light, and the light will be converted through charge coupled device into the image. Remember, the image that will be formed is going to be flipped and inverted into an 80 degree, okay? And that flip and inverted image will be corrected electronically. So the thickness and the height of the output passport. The height of the output passport is mostly 2.5 centimeter and thickness 4 to 8 micrometer. So the thickness of the input passport is 300 to 500 micrometer. Remember, the SI unit, 300 to 500 micrometer, and the output passport is 4 to 8 micrometer. X-ray getting converted into light, then light again into electron. Electron converted again into light. A lot of issue. So what could be the possible problem that we might encounter? Let's start with the pinpoint distortion. This is a distortion whereby the edges of image becomes like both from outside due to unequal electron path, due to unequal magnification across the field. So central region mostly become undistorted, but the peripheral becomes stretched out. So to correct such problems is caused by the input curved input pathway. Remember this because they may ask you in exam. The software correction is the method that we can use to correct these issues, or we can just discard or replace the image intensifier by using flat panel detector. What could be the other part? Because we can have another part of it which is called like uh, S distortion. The S distortion is a bit of due to external magnetic fields. This is common in exam. So we have external magnetic fields such as MR nearby could make, or if MR device is nearby the polar unit, it may deflect the electron. The electron have been helped by three electrodes. The first G1, G2, G3. So the G2 is helping with the focusing the electrons as they travel, while the G3 is main our flux gain, which is accelerating the electrons. So at that time, because S-shape waving, warping of straight line across the image, um, the main cause is due to the external magnetic field bending the electron trajectory to form a bit of S shape. It's not up to it's more mostly a bit of shape carbon. So what are the main methods? We got mill metal shielded around the image sphere, or avoid strong magnetic field sources nearby the device. The X shape. The next form of abnormality or distortion that may happen to image sphere is called veiling. So what is veiling glare? So in the veiling, as you know, as a light scatters within the image in the sphere too, reflection of glass envelope that might happen out the window. So reduces image contrast. Dark areas appear lighter than they should. So area that is should be a bit darker might be lighter, brighter in the output or the image. The main cause is due to internal reflection within the vacuum of the tube. So what would be the best method to prevent this? Anti-reflection, coating, aperture control, and the others. So what would be the next one? The next one is vignette. Vignette is a bit common in exam. Mostly, one, two, three, you say vignette in your exam. So what is vignette? So vignetting image brightness falls off at the edges compared to the center, meaning that the brightness at the edges will be less than that of center. Central, or to say in another word, central brightness will be higher than the peripheral one, caused by electron optics geometry. Peripheral electron travel longer path and are less efficiently focused by the J2 electrode. So this is the main cause of the vignetting. So how can we solve this issue? Using can you flat panel detectors to eliminate this, or okay, flat field correction. So the main method of preventing vignetting is using a flat panel detector. Magnification mode reduces input field, mostly usually increase patient dose. Flat panel detector eliminates most of the distortions related to image intensifier. So everything now is pointed to flat panel detector. Let us talk about flat panel detector. What is a flat panel detector? Panel detector, the remnant X-ray is going to be converted into digital data for real-time display, as you know, the fluoroscopy. So we are using scintillator. Scintillator is a bit made from also cesium iodide, similar to the output input phosphor of the image intensifier. So that scintillator is going to convert the X-ray into light. And then the light is going to be converted by photodiode, not photocathode. So photodiode, photo means light, diode means electric charge. So not photocathode that will convert light into electron. And this light is going to be converted into electrical charge. Then that electrical charge will pass through a TFT. The TFT array is going to convert and charge read out pixel by pixel, going to read all the charges, the electric charges, pixel by pixel, and then using analog to DSA, the analog to digital signal, convert them from analog to digital, and then display real-time image. What are the main advantages of a flat panel detectors over the image intensifier? So all the distortions type, so no pin cushion, no S distortion, wider dynamic range, beta DQA, and at higher dose rate, and simulates digital workflow, compact and lighter weight. No vacuum tube generation, no no glaring, nothing. So, but what are the main limitation? Detector can lag to display image. A digital signal from the prior frame might be become ghost into that. And then we can have electronic noise at low dose rate, calibration, artifact, the gain offset, and others. So that these are among the limitations related to the flat panel detector. Detectors eliminate all the geometric distortion related to image intensifier, but we can have lagging, ghosting, calibration needs, and lagging can obscure fast-moving structures like guideways. So these are among the implications of using flat panel detectors also. But overall, they are better than the event inspire. So now automatic brightness control. Sometimes we got thin patient, we got thick or larger patient. So the automatic brightness control help and the exposure help to modify the settings so that we can have better and approximate brightness for better image and better display to have better diagnosis. We have thin patient, the X-ray coming, we have the X-ray, Roman X-ray, using platinum, so we have constant. But what about if we get larger patients? Would it gonna be the same? No, because what will happen is that the MA will become more because we have to increase the MA, the photons, the thicker patient. We have to increase KBP because the larger patient have more beta penetration. And in that, but we will have less contrast. So we increase MA to overcome the less contrast or the degradation of the contrast, the implication of the increased KBP. The longer exposure also, because larger patient also, so that patient dose is going to increase. This is the implication. So what triggers high output? Mostly larger patient, oblique projection you're taking, RAO, right, anterior oblique, RPO and others, so left, right, taking oblique, magnification mode, mostly increase dose to the patient, their dense body, removing grid because of the so what calls scatter reaching the detector also. So all these are going to increase cause high or trigger high output. For that, we mostly always monitor the those area product DAP and fluoroscopy time as it goes on, because to know the cumulative dose you have been used, so that to know the exposure, when to time the exposure, or if you need to repeat the exposure to get support, to get time and know the dose you have been used for the patient, also for yourself, for the safety measure also. A constant looking image does not mean constant dose, because anything that happen that may trigger the increased higher dose may lead to increased dose, but you not see it. So that constant doesn't mean you have constant image and your constant dose. So you have to check DAP and others. So what image quality and this control? So you have to understand to collimate. Uh, Really, fluoroscopy is one of the field or one of the investigation or radiography methods that you have to take measures for collimation. Because if you're looking for the vessel in the lower limb, you shouldn't just take the whole body part. So collimation will cause less catheter and less irradiated area, and thus go down, and that will improves contrast. Last image hold is a method that we're using to freeze the last frame on screen so that no additional radiation dose is used while we don't need it. So magnification, mostly we're using zoom so that you can zoom in and out on the last image so that you don't need the dose or magnification. The detector patient gap. The more detector, move the detector close to the patient so that that will be the main remnant X-ray coming to the detector will reach the detector very fast and very easier than taking the detector away from the patient, and there'll be less magnification as you are decreasing the object to detector or object to image distance, and better efficiency, better sharpness of the image, and also sometimes you are decreasing the magnification, you are decreasing the geometric sharpness. Source to distance, source to skin, also distance. Keep to a bit far from the patient so that you minimize the entrance surface dose or entrance skin dose, ESD. That will go down also. Dose mode selection, low, mostly take low, normal, high quality. So balance the image quality, but dose, add filtration, sometimes you add cover, The copper will help to filter harden the beam so that it becomes more intense, removes low energy photons. Grid selection and scatter grid is used to improve contrast, to remove the scatter and also increase, well, at the same time to increase dose. So you are just monitoring everything. That's image quality, very important. So you are monitoring everything. Sometimes you get better quality. The quality equals temporal resolution plus contrast plus noise plus dust control. So you have to control everything. You have to take everything into perspective so that you get better image. Does that image hold use more radiation? No, of course, because display last image. So without another exposure. Remember, protection depends on the classic triad, that TDAs. You have time, distance, and shielding. So time, the less time you take, last image hold, very important. So you take the less time you take, the better the dose optimization, especially if the other parameters were kept constant. So, and also distance, inverse square law. That's, remember, you shouldn't go close to the primary source or to the image. Be a bit far from the image patient as possible, and do not put your hands just towards within the primary beams. Okay, never place your hands in the primary beam, the remnant beam, because they're very strong. And remember, then after distance, you got shielding. Shield yourself by then such as light aprons, far-away shield, light glasses, ceilings or panel shield. Sometimes they are saying also you use the main, even the source of the patient, if it is under table or over table. The undercoat mostly gives a lace dose to the eater, because the cut is not reaching the sorry, it's not reaching the detect, it's not reaching the operator. So these are among the approach that we use in order to prevent ourselves and also to prevent high dose to the patients. So now let us move to the last part of this lecture, which is angiography. Happening in angiography, there's a digital subtraction angiography. So what we do is that we started by capturing mask image with our contrast, pre-contrast image of vessel. Then we inject iodinated contrast. So why are we using this method? As we mentioned on lecture 1 and 2, after injecting, contrast such as iodine has very high atomic number and high energy and density, very dense. So at the X-ray primary beam coming, only part of it will be absorbed by that injected iodine inside the vessel. Most of it, almost 92 to 95%, is going to be absorbed. So only few remnant X-ray remnant photon or X-ray is going to reach to the detector. So detector will assume, and there's a bit no less photon is going to cast that as white or brighter, that going to be bright area. So we are using that to say base as brighter areas after subtraction, so that we can see there is obstructions, stenosis inside the basal. This is a very important method. So we started by this. You remember photoelectric, it has so the iron has high density, and remember the photoelectric effect is directly proportional or increases with the atomic number Q. So we have very dense material with a high atomic number. So the photoelectric will help us to see the bezel as brighter because less photon is reaching the detector. So what now? After that, what will happen? We'll got the image, we then subtract the, after injection the contrast, we inject the contrast, we then subtract the contrast, we subtract, sorry, the mask image from the contrast image. So we have a pre-contrast, that's mask image, then we inject the contrast. After injecting the contrast, we subtract the mask image from the contrast, that it will remain only the contrast, that's the DSA. So you subtract it. After subtraction, you get your vessel map. So like I can say, you can make diagnosis, the background anatomy will disappear. What happens if patient moves between mask image? So what will happen is that we have image taken and the patient move. There's gonna be misregistration artefact. Anatomy fails to subtract clearly because the patient moves, and that will give us some misconception, misrepresentation of the image, and all the basal, maybe less diagnostic value. We may need to do again. Nowadays, mostly we are using MRA and others, CTA, MRA. So, but still, just the basics, and it is important to understand because of the exam. You then you capture mask image free contrast, you then inject contrast, you subtract the mask from the contrast, then it will remain only the basal map without anything, with no background anatomy. You will see only the basal. Also, monitoring in fluoroscopy is very important. It needs multiple metrics. So time alone is incomplete. So you have to follow a lot of things in fluoroscopy. You have time, you have KPA, DAP, PKA, so dose beam area product, cumulative air kerma, skin dose, dose rate, and others. The patient taking scatter protection tools. You start using, tube under couch, mostly scatter mainly downward. It will not go to the patient or to the staff. Also, start a bit away from the patient. Okay, stay away mostly for the distance. And then we have use your thyroid shield, lead glasses, mostly 0.75 millimeter of lead, lead apron 0.25 to 0.5 millimeter for protection of the body. Ceiling suspended shield, upper body shall be shielded, and for ceiling suspended, but mostly we're using under couch sometimes. Lead drops of patient distant from patient, collimation, avoid hands inside the primary beam. These are among the methods that we using to protect ourselves and also to minimize or optimize the dose to the patient. Fluoroscopy time alone does not solve the issue, as I mentioned. Does not describe patient dose, and mostly, time alone does not describe patient dose. So still, you have to try to optimize. Okay, you optimize the procedures that by using large image hold and others, so that zooming instead of magnification, etc. So that you can minimize also dose to the patient. Now, let us recap. So, fluoroscopy, we have source from source to the patient, attenuation, contrast. We have detector, the image formation, subtlety, and dose metrics. And as you start to understand, this is the last part, the last lecture. We have gone through both of the X-ray. We have the X-ray coming inside the tube. We have photo mix the patient, what have been happening, infraction and attenuation, controlling the journey, filtration, collimation, so to minimize the catheter. We have catching the beam using CR, DR, digital information, making it diagnostic for factors affecting image quality. And then when the image lies, the artifact, error, distortion, quality assurance, mammography, which is using low energy contrast to capture or to image braced. This is the last one, which is fluoroscopy and angiography. So remember, we're going to do another lecture, which is gonna be like recapping everything. Remember the RadSound framework. From the source, patient, signal, detector, image, optimization, and subtlety. We follow the source, follow the signal, master the image. See you in the final part, which is going to be just a small part. It is just a bit of recapping of everything. Thank you.